All right, so 23 is a conservation of angular momentum problem. So what I mean by that is that the angular momentum that we have to begin with is going to equal the angular momentum that we have at some later point in time. And the reason for that is it does say here, assuming that no external torques act on the system. So if there was an external torque, that would be a reason why the angular momentum would be different at the end than it was at the beginning. But if we're assuming that no external torques act, then really the only things that affect L are I and omega. So I can take this equation and replace it with I O omega O equals I F omega F. So I only have 4 variables to worry about. Once I know 3 out of the 4, I can solve for the 4th. So looking at the problem, it says a baggage carousel at an airport is rotating with an angular speed of 0.25 radians per second when the baggage begins to be loaded onto it. The moment of inertia of the carousel is 1,600 kilogram meters squared. So that would be the empty carousel. It already has inertia before any bags are on it. Then it says 10 pieces of baggage with an average mass of 18 kilograms each are dropped vertically onto the carousel, so from above, and they come to rest at a perpendicular distance of 3 meters from the axis of rotation. So if I'm showing this from above, if this is the carousel, then what we have is we have all of these bags that are being dropped onto the carousel. And they all, let's see, 1, 2, 3, 4, 5, 6, 7, 8, put 1 here, 9, and 10. They don't have to be equally distributed. They're just all at that distance away. So we already have angular momentum for the carousel itself, and now we're going to get we already have a rotational moment of inertia for the carousel itself. Now we need to add in this for what the change is, how much new I we have compared to when it was empty. So if I list my facts, I'm going to have that the original angular velocity is 0.25 radians per second, and the original I is 1,600. That was the empty carousel, kilogram meters squared. And the question is, find the final angular speed. So the final is the unknown. Final angular speed is the unknown, which would be in radians per second. So what we need to do is figure out the final I. That's the only variable. You look at the equation. We know this and this. We're looking for that. And so if we know that, we'll know these 3, and then we can solve for that. So I need to solve for that. So the I final is going to equal the I original plus whatever we get from the bags that are on there. Now all the bags are at the same distance away. So actually the formula is just as if we had a yo-yo, swinging a yo-yo around by a string or a ring. Okay, there are gaps, but it doesn't really matter. So if we look at here, there's gaps. There's no mass here. There's no mass here, here, or here. But in terms of all the mass is located at the same distance away from the center. And let's see what that was again. That was 10 bags with an average mass of 18 are 3 meters away. So this distance right here is 3 meters away. And so if we have 10 bags with an average mass of 18, then we have a total mass of 180 kilograms on the outside here. So 180 kilograms is on the outside, and it's that distance away. So as far as the formula, I'm going to have the original I plus mr squared. That would be the formula for the inertia, moment of inertia created by the bags. So we're going to get 1,600, because that's what we started with, plus mr squared. So it was 10 bags with an average mass of 18. So a total of 180 kilograms of mass, all located at a distance of 3 meters away. So if you solve that, what do you get? $3,220. So it about doubles. I mean, it's a little bit more than doubling it, but what that means is that this amount right here, if this is 1,600 and that's 3,220, then this is 1,620. So the mistake that I see people make on the test is they'll put their original as 1,600 and then they'll put their final as 1,620. So they'll only have a very small change in inertia, so there'll be a very small change in angular velocity. Don't make that mistake. So remember, when we add bags to a carousel, well, the carousel already starts with some inertia. It's not starting at 0 when we add the bags. So don't forget to add in the moment of inertia of the empty carousel plus the moment of inertia created by the bags. So now that we have all those numbers, we can just plug it into this formula right here. Just rearrange to solve for that, and we will get omega F equals I-O omega O over IF. So looking at those numbers, it looks like the angular velocity is going to be about half. Because if I double the moment of inertia, and it's about doubled, then we're going to get about half of the I. So we're going to have 1,600 kilogram meters squared times the original angular velocity was 0.25 and that's all going to be divided by 3,220. And when you solve that, what do you get? 0.124. So 0.124 radians per second. All right, any questions on that? So the formula you're working with isn't that complicated. I mean, it's just I-O omega O equals IF omega. Once I know 3 out of the 4, I can solve for the 4th. So just be careful when you're solving for the IF that you're going to add, that it's going to be, you're starting at whatever the original moment of inertia is, and then to that, you're going to add in the moment of inertia created by the bags. All set? Yes?
How come the big carousel